Hey, Dr. Clark here with another preview video. This time we're looking at section 1.3, modeling with differential equations. Let's get started. So we're going to talk about math models here, and just a definition. A mathematical model is a description of a system, phenomenon, or process using mathematical concepts and language. In this class, we're going to focus on mathematical models that are built from differential equations, of course, but there are other mathematical models out there. So some of the key aspects for math models is we want to make clearly stated and hopefully reasonably accurate assumptions, describe all the variables that are used, both independent and dependent variables, and then keep track of which ones are independent and dependent. And then, of course, talk about parameters. And parameters are sort of like constants that show up in the model, but they can be played with. So you could say, well, we've got this parameter, which is the temperature, but then we could turn the dial on what the temperature is. So it's a constant that's not constant, I guess, if you will. Or it's a constant that could take on different values, right? Or maybe gravity. Well, here's my model of how this ball flies through the air, but of course, if that ball flies through the air on Earth or if it flies through the air on Venus, the gravity is going to be different because of the different masses on the planets. So a parameter like the force of gravity might show up in the model, and you just need to pay attention to where you are. What actually gravity is. And you can normally think of gravity as constant, but in some sense it is a parameter. And then the last thing is use these assumptions and all these variables, package them together, and then derive equations that relate the quantities that tell you how one quantity is connected to another quantity. And of course, in this class, we're going to be using differential equations to connect those quantities. So that's what a math model is. And then just kind of abstractly, when you think about what's going on with modeling, I want you to keep in mind two quotes. So first, Einstein says, make everything as simple as possible, but no simpler. And I think that's a good thing to keep in mind. We don't want to have things that are so complicated we can't understand them. For example, like even in this coffee cup here, there are, how many atoms? I don't know, 1 trillion atoms, or probably even more than that, atoms in the coffee cup. But are you going to pay attention to the location of every single atom? Well, that would make things incredibly complicated. It would be more true in a sense, but it would also obfuscate all of the meaning out of it. And so you can just sort of say like, well, it's just a coffee cup, right? And then you're making it as simple as possible, but no simpler. And then Bach said, all models are wrong, but some are useful. And that is another great idea. Anytime you're modeling something, you're simplifying it, right? You're saying, well, let's pretend that these equations describe this. Well, they probably don't perfectly describe it. So everything has some amount of inaccuracy compared to the objective reality of the world. But a good model can still be useful, even though it is, in some sense, wrong. All right. And then, so when we talk about modeling, you have the real world as it really is with atoms and quarks and temperature and heat and photons and everything. And we formulate that, we simplify it, we condense it down into a mathematical model. We then do analysis on the model and get results and predictions. So maybe you have, there's clouds and there's wind and there's pressure and there's temperature, and we formulate in that information into a mathematical model. The analysis gives us a result which says, actually, tomorrow it's going to rain. And then what we can do is we can say, well, we go back and we say, did it actually rain? And then we can say, was that prediction actually correct? And if your model generates an incorrect prediction every single time, then you've got to go back to your model, make a new model, do analysis, get predictions, and then check that with the real world. So it's really a process of continuous improvement. And you want the model not just to be randomly made, but to be made from principles that make sense. Okay, and then just to kind of put some context on this again, the dry ice model we talked about a few days ago. So we had some variables like time, and then we said, well, the mass of the dry ice at a particular time. So this time is, of course, an independent variable, but the mass was dependent on time. So if you knew what time it was, then maybe that would tell you what the mass was, right? We were tracking the mass over time. So independent variable for time, dependent variable for mass. K showed up as a parameter in the model, the heat transfer proportionality constant, right? So we said that the rate of change of the mass was proportional to the mass in the first model, the exponential decay model. And then later on, we said that the rate of change of mass is proportional to the surface area. And of course, that surface area calculation came from sort of a dimensional analysis. That's where the 2/3 came from, surface area being 2 dimensions, volume, and therefore mass being 3-dimensional. But that K shows up as some sort of proportionality constant relating to the fact that we had dry ice dropped into water. If we had dry ice dropped into air or dry ice dropped into acetone, maybe we would get different K's there, or maybe dry ice dropped into warm water or dry ice dropped into lava, right? That K is proportional to having to do with the materials involved. And then C showed up in our solutions when we solved these differential equations. You noticed a C came out in the solving process, and that turned out to be a constant relating to the initial mass. So that's sort of a constant. It's not really a parameter in the sense that it shows up in the model, but it is a constant that is connected to reality. Okay, so hopefully that gives you a sense of what a model is, what the point of a model is, and then an example of a model, and then we'll get into some more details later of other mathematical models that you'll see in this class, modeling things other than dry ice. So hopefully that was helpful, and we'll see you next time.